All right, let's talk about networking. So when we take a look at all the things that we are trying to accomplish with getting into IT, it's really going to come down to making sure that everything connects. So we already talked about kind of what a network is and some of the fundamentals to get it up and running. And I told you there was more detail, and here it is. So this is one of the longer lessons that gets into some of that nitty-gritty as far as components and port numbers and how to get connected, but it is worth it and you need to be taking notes. So don't get disheartened. And just because I like you, I've actually cut this in 2 different parts. So you won't have to listen to me for an hour and change talking about it straight. We'll take a little break in between and then come back to it. So the first thing we need to take a look at is the NIC, the Network Interface Card. And there's another really important part of this, and that's that physical network address, i.e. your MAC address. Now, this is one of those important connector cards that you have on your motherboard, and this is how you get on the network. So you've got the network connection port itself. All cards are going to have either 1 or more ports configured just to give you network access through a network cable, aka Cat5, Cat6. So some older cards have different types of ports, but the newer cards are all standardized and use the RJ45. Now your physical network address, again, is your MAC address. This is your media access control, and it is your globally unique physical address. It used to be called a burn-in address because it was literally burned in. Now we just use stickers. It's a little less harsh. And of course, you have your status indicator lights. So most adapters have a link light and an activity light, and some of them have a speed light as well. A link light's just going to let you know if there's a signal from the network itself. If it's not lit, usually there's a physical issue. An activity light is the one that actually flickers whenever packets are being sent or received. So as long as it's flickering consistently, then you have things going back and forth. You have data. But if it's flickering constantly, you might have too much data going on, meaning that it's overused and you might need to increase your data throughput. The other thing is you might have a lot of noise on your network, or the device itself is creating noise. So a healthy amount is flickering when you're sending or receiving data, but a constant high rate of flickering might mean that there's too much going on. Now the speed light, like I said, is optional. And this is the whole purpose of it, is to show whether the adapter is operating at 10, 100, or 1,000 megabits. Now 1,000 megabits is the equivalent of a gigabit connection, so that's a much faster speed. Now, do you need to know the exact rate of all these lights and all those specifics? Nope, not necessarily. But you need to know that there should be lights and which ones should be on constantly, meaning it's just on, the actual physical device is working, aka the link light, and that data is being sent and received, aka the activity light. So beyond that, we've got our actual card. Now we need to plug it into something. And that's going to be our Ethernet cable. So we have the most popular way sitting here as far as getting connected to our LAN, our local area network. And that most popular way at this point is Ethernet. So this is the most conventional, most popular, the one you'll come across most often. Now that doesn't mean it's the only. You can still use coax, and of course we're moving into fiber pretty quickly for the corporate side, to be honest, and even in some home use. But Ethernet is still the most popular and what you'll come over or come across most often. So inside of your Ethernet, what in the world is going on? Well, there's some twisted pairs of tiny cables inside of there. And inside of these twisted pairs is copper, meaning that coax is not the only thing made of copper. It's just usually what we think of first. But Ethernet is actually a copper medium as well. Now there are 8 twisted single individual wires that make up 4 twisted pairs. And the higher the twist rate, meaning the tighter they are twisted, means that there's a less likelihood or a decreased amount of this thing that we call crosstalk. which is pretty much a decrease in your signal strength over longer and longer periods, or feet or meters, or however you'd like to measure your cable. So twisted pair is considered, or is a type of cable that has 4 twisted pairs, but that's just the most popular when we're talking about Cat 5 and 6. Cat 3, meaning telephone wire, that's actually a twisted pair as well, but there's only 2 pairs inside, which is a total of 4 connectors. So it has less ability to transfer as much data at a time. We are going to focus on Cat 5 because that is the most popular. Now what you're seeing on screen here is what we consider UTP, which is unshielded twisted pair. That means that there's no shield on it, which is just another layer to help prevent any type of interference or noise being able to distract or distort the cable frequency. All right, so I said Cat 5 is the most popular, but there are different categories. That's what CAT stands for, by the way, is category. So Cat 3 is telephone wiring, and Cat 5 is the most common Ethernet. And Cat 5e was created to replace just the normal Cat 5. Now, what are the differences? Cat 5e can operate at a much faster speed. We're going from 100 megabits up to the absolute theoretical maximum, which means in a perfect world, 1 gigabit, or the equivalent of 1,000 megabits per second. Now, Cat 6 is up and coming, and it's still expensive, but you will see it more and more often between switches and routers that need that ability to transfer a lot of data at once. And the maximum speed here is 10 gigabits per second. Now, again, that's a theoretical speed, so this is in a perfect world. Short cable, no interference, everything is good. But it still has higher speeds than anything else in the Cat 3 or 5 range. Cat 6A, or Cat 6 augmented, is a thing as well. And the only difference between Cat 6 and Cat 6A is the frequency itself. So that's really still the same maximum theoretical throughput, but it's operating at a different frequency, which means it's less likely to come across interference or noise. Now, Cat 7 is pretty much the latest and greatest standards, but you really probably have not seen it. Now, it goes above and beyond in speed. As you see, it says 10 gigabits per second plus, which means it just goes faster. And that's all you need to know for your test. But in real life, what you need to know is that you can stretch Cat 7 much further in regards to laying a longer cable out without a decrease in signal strength. And it has improved crosstalk noise reduction pretty much just built into it, which means it's less susceptible to noise or interference, which causes issues in our data. So when you put together, and at some point in your networking career, if that's the path that you go, you will do this thing called terminating Cat 5 or Cat 6. And terminating just means making it, and all making it means is putting a connector on the end. So terminating category or Ethernet cord is just putting an RJ45 at the end. And that means aligning those 8 little wires inside in the right order, getting them to the right length, getting the connector on, and squeezing it down so it's there semi-permanently, meaning that you can't just shake it and it'll fall off. So there are 2 different orders that you'll be concerned with here. And I'm actually going to pull up a picture and show you the 2 different ones. But depending on which order you use is the standard per se in regards to the order of the cables themselves. So you see it says 8 pins and it says white, green, which is the W/ means white. So white, green, green, white, orange, blue, white, blue, orange, white, brown, brown. That is the order for T568A. And that's at this point what we consider the legacy standard. Let me show you a comparison chart that has both T568A and B. B is what we consider the current standard. So take a look at this chart that you have on your screen. You see the order of T568A. Now what I want you to do is take a look at the order of T568B. They both have 8 pins and they both end in white, brown, brown. That will never ever change. But the order of the first sections change. Now take a look in the middle as well and you'll see blue, white, blue are in the same place for both. So what is actually changing here? Pins 1, 2, 3, and 6 change places to go from B to A as well as A to B. So take a look up here. Pins 1 and 2 on B are white, orange, orange. And if we trade them and put them in the places of pins 3 and 6, that means white, orange, and orange will go in the places of 3 and 6. We're taking number 1 and 2 and putting them in 3 and 6. And the opposite, of course, will take 3 and 6 and put them in the place of 1 and 2. So you need to know this for real life as well as your tests, not only your A+, but when you get to your Net Plus, this will be very valuable information. Pins 1, 2, 3, and 6 change places to go from T568A to B or B to A. All right, so let's continue on over here. So some options or upgrades per se to our cables or our plenum. So PVC or polyvinyl chloride, which you'll just want to call PVC, is the less expensive, flexible, rubber-like plastic. And that's what's around most of our twisted pair cabling. But if for any reason it catches fire or just gets warm to the point that it starts to melt, it can actually release nauseous, poisonous gas. And that's a problem in schools and hospitals and life in general, to be honest. So newer buildings have the requirement to use plenum, especially when we're going through ceilings or structural differences and any space that has ducting in it. So suspended ceilings or structural ceilings, if we have raised floors or fire break walls, it is a requirement now to use plenum cabling. And it's a special type of jacket or outside of the cable per se that doesn't give off any nauseous or poisonous gases when it burns. So it's a much, much safer option. So let's jump back into that T568AB thing. Now there's a lot of words on your screen, but let's take a look at what matters the most. T568A is a legacy standard. It was used in commercial buildings and cabling systems, and we used it for all kinds of networks. Data, voice, video, didn't matter. But T568B is the new standard and the preferred cable type. It has better performance levels, and we can use it from home-based and office-based networks. It also is the one that we use with shielding, meaning that we give it an extra layer inside the cable to make sure that noise or interference or other data cables can't necessarily distort the data that's going across. All right, so don't worry about the other standards. A and B is where I want you to focus the most. So we've spent a good amount of time on Ethernet, but there are other kind of cables that you need to be aware of. And coax is something that I am sure you've come across in your life. Now what you're looking at is the same type of coax that hooked up your TV set-top boxes that's connected to your router at home. And we just call this stuff coax. It's a copper cable that has that central core in it, a single copper conductor. Now there is braided shielding, and inside of that there is non-conductive insulating coating. And the whole point of that is to make sure that, again, the data is not, what's the best word here? Not interrupted or distorted by electromagnetic interference or EMI. So we're going to always want to shield our data as much as possible from any outside resources or disturbances from causing issues. So there's more than one kind of connector that you can put on the end of coax. You're used to at home what's called an F connector, and that is the most popular and pretty standard for at-home implementation. So it's used to connect cable TVs. You can even use it for FM antennas and of course to your modem. But there are two other kinds that I want to talk about here. And the first is BNC, or bayonet needle Concealment connector. This was used with what we call ThinNet, which is an older type of media that we used for networking. Now, RG58 and RG59 connectors are also in that legacy category. RG59 was used for cable TV transmissions way back in the day when you had a maximum transmission speed of literally 10 megabits per second. And now we're way beyond that. So BNC connectors are still used in radio and some like aviation implementations today, but you won't see it very often outside of that. Now, an RG8 connector is what we use for this thing called ThickNet. It's actually a thicker coax cable than the normal one that you've probably been able to interact with before. You really don't see it today. This stuff was really expensive and it was stiff because it was so thick, so you couldn't really bend it around corners. But we used to use it as the backbone cable for network installations because it could, at its time, pass along a lot of information, meaning it could handle a lot of data throughput at any given time. So the faster version of all of this, the new, latest, greatest, is fiber. You hear about it in the news, you want it in your house, and it may or may not be coming to you very soon if it's not already there. But there is no copper here. The core of fiber is made of glass or plastic, and it is super, super thin. And when I say thin, I'm talking it's measured in microns. So take a look at your fingernail, and if you have really thin fingernails, it's thinner than that. And if you have really thick fingernails, well, it's way thinner than just the end of your fingernail looking down at your finger. We're talking the thickness of a piece of hair or smaller. Anyways, how does it work? So this tiny, tiny piece of glass or plastic has light going through it. And there's two different kinds of fiber, single mode and multi-mode. Single mode is going to allow one piece of light at a time, and it's going to be able to operate across really long distances. Now, multi-mode will allow more than one piece of data, aka light, to enter at a time, but it has to enter at a different angle so that the pieces of light or pieces of data don't necessarily overlap. All right, so the core is either glass or plastic, and then you have a lot of protective layers around it. So you see cladding and coating, which are going to literally mean they're plastic surroundings to go around the core, just to have a buffer. After that, you've got the strengthening fibers, which most of the time are made of Kevlar or something very similar. Then, of course, you have your outer jacket or your armor that protects all of the assembly together. Now, light pulses from a laser or an LED are passed through the core, and that's what carries the signal. And the cladding itself is what reflects the light back into the core, which increases the distance the signal can travel without needing some type of regenerator in the middle. Now, fiber is still expensive, even though the price is definitely coming down. And it's also pretty fragile because you can't bend it at 90 degrees or anywhere near it because, of course, it's glass. And what happens when you try and bend light 90 degrees? Well, it usually doesn't work out so well. So you have to be careful when you're installing this stuff. But it is fast and it is extremely reliable, and we can use it over long, long distances. To be honest, you have fiber, or I should say we have fiber, that actually stretches across the entire ocean. We have fiber connectors that connect from New York over into Europe across the entire Atlantic. Now, of course, there are some repeaters used, and more than a few, but we have some single core or single mode fiber that stretches across an entire ocean. That's a huge deal because getting data from here to there used to be a major challenge. I mean, before all of this IT stuff, it was on a boat. Now we're talking milliseconds to be able to just transfer stuff from here to Europe as if it was always natural and just in the air. All right. So I want to get into a little bit more of the particulars on how single versus multi-mode works. And here I'm going to focus more on single mode and what is called stepped index multi-mode, because those are the two most popular for implementation and, of course, your tests. So single mode fiber carries a single optical signal, one at a time. It has a much smaller core that only lets one beam of light pass at any given time. And it's usually, as far as the light or the laser, is operating in an infrared portion of the spectrum. So it's good to know, but that's not going to affect you at this level until you start implementing fiber yourself. You just need to understand one signal or one piece of light at a time. And you need to know that this is the one that stretches the longest. Now, step index multimode contains a core surrounded by the cladding, just like the single mode, but the core itself is usually much, much thicker. Now, when I say much thicker, we're talking about maybe 70, 80, 90 microns, which is still super tiny for us, but thick in regards to the piece of glass when you compare it to single mode. So how does this stuff work, and how can we transfer more than one piece of light at a time? Well, step index fiber uses what's called total internal reflection, and that's what traps light, and it's just going to make sure that they're a different entry angle. So you see one piece of data, and I'll try and do this with my mouse. One piece of data has entered coming down and then goes back up and then down and goes back up, and it'll continue. And you have another piece of data here that has actually gone up first and down second. Now they look like they're pretty matched in regards to where they hit or how often they hit the sidewalls or cladding, but they're at different entry angles, which means they'll never actually hit both at the top or both at the bottom at the exact same time. So that means the data can make it through. Now take a look at this second piece of data or light that's entered in our example. The angle that it's entered at is different and actually hits the cladding at a later point, a physical later point. It's gone further before it bounces or reflects down to the bottom of the cladding and reflects again. So that's all about the entry angle that we're reviewing to make step index multimode work. All right, graded index multimode fiber is a little bit more complicated, but it is something that has a different frequency. That means it has more bandwidth, and well, I don't want to go into too much here, but it possesses variations in the actual core glass to compensate for the mode. So the grade index mode, which means the path and the lengths are different, but they'll still come together and cross each other at the same point every time. Let's stop there for how grade index works and talk about connectors. There are a lot of different types of connectors for fiber. Now we saw one kind of connector for Ethernet, RJ45, unless you have Cat3, which is RJ11, a little bit smaller. And I'll put those on screen as well so you can take a look. Now, when we looked at our coax, we were taking a look at what kind of connectors? RJ8 and F connectors and B and C. All right, so we want to take a look at all the kinds of connectors that are for fiber. And like I said, there are a few. So the first one you see there is ST. And ST stands for straight tip. Straight tip is used to connect multi-mode fiber. Multi-mode. And they're very similar to BNC connectors from coax. They have a straight ceramic center pin and a lockdown per se, which means they're going to grab on or latch on to the wall port or female side of whatever you're connecting them to. They are one of the most popular fiber connectors, and again, straight tip goes with multi-mode fiber. Next to that is SC, subscriber connector, or what we usually just call a standard connector. It's a box-shaped connector and it snaps into place. And they're really mostly used in what's called a duplex configuration, which are two fiber connectors, and they come together within your SC connector. And this is used with single mode fiber. Now I want to stop here and talk about duplex. Now the first time we heard this word is in printers, both sides of the page, right? But duplex at its core just means two directions or both. Now, when we talk about light, aka fiber data transmission, you can't send light both ways at the same time. If you send light in from both directions of the glass, then they're going to at some point come across each other and your data is going to be corrupted like crazy. So when we implement fiber, we actually implement two strands of fiber, one for receiving and one for sending or transmitting. So sending and receiving are the two lines that we're always going to implement, which means you have unidirectional travel, or one direction at a time through fiber wires. And that goes for both single and multi-mode. But I wanted to bring that up because your standard connector, your SC, is meant for a duplex configuration, meaning two fiber lines are terminated. All right, the FC is not as popular, but you have to have something that's much stronger and heavy duty when we're in an industrial setting. And that's what this FC is used for. And it stands for face contact. It's similar to the SMA connector that's below it. And I will get to that description here in just a second. But FCs are heavy duty and they are meant just for the industrial setting. An LC is a local connector. It's a little bit smaller of a form factor, and it still has that center ceramic piece that's in the center, right? But it's good for both single mode and multi-mode fiber, and it's about half the physical size of a standard connector or straight tip connector. So it's very similar to an RJ45 in the fact that it has a little latch that pretty much just clicks into place in whatever port you're putting this into. An SMA, or a sub-miniature type A, SMA, is pretty similar to an ST in the way that it looks, but it's threaded, just like an F connector for your coax. And you need to be able to not only thread, but then lock the connector into place. These are usually used wherever water or environmental factors are an issue. So if there's an outside connection, this is probably what you're going to come across. And the last one we'll talk about here is what's called an MTRJ, or a mechanical transfer registered jack. Sometimes they'll just call it a fiber jack for short, but it's a snap to lock type connector, and it's only used with multi-mode fiber. It's pretty easy to use because you just snap it into place, kind of like an RJ45. And it is meant for two strands of fiber. So again, that duplexing is in place here. Whew, that was a lot. Which ones are you going to come across most often? Well, that will be your ST and your MTRJ. I'd say those are the most common to see in real world and test settings, but I want you to be familiar with all of these because if you're in a warehouse of any kind, you're going to come across that heavier duty FC connector. And if you're working outside, then you're probably going to come across that SMA connector. So it's not bad to at least familiarize yourself with the different options. Now, that's wired, but let's talk about wireless. Anything that can transmit a signal without physical wires is considered wireless. That's Bluetooth, radio, satellite, doesn't matter. And of course, we need to talk about how to connect to this stuff. Now, is wireless truly wireless? Well, my first answer is no, and that's why I come back really quickly to wires. To make all of this work in a home or business, you need an access point. And a lot of people forget that access points are wired behind the scenes. Even though they're just kind of floating up there on the wall or the ceiling, behind that is a wire that connects to a switch and then a router. So you need to make sure that you remember that there are wires involved in all of this good stuff. Let me stick with that for just a second. So we're getting online and we have all this stuff in place. So now we need a protocol. We need rules. We need configurations. We talked a little bit about the OSI versus TCP IP model, and you need to understand that why the TCP IP model exists is for troubleshooting, assessing, configuring network connections. That's really what it's all about. So everything that we do needs an IPv4 address. Now, we do have IPv6 addresses, and those are getting much more popular as we come into the new age of the internet. And that's because we ran out of IPv4 addresses a long time ago, so we had to get a new system. So what is an IPv4 address made of? Well, it's made of ones and zeros, and that's binary. Now, we're not going to learn how to count in binary in A+. You definitely don't need to. But you do need to understand that every IPv4 address is made up of what are called octets, which is 8 ones or zeros. You see it up there in the binary formatting of the IP address. But how we see them and how we type them, how we say them, is in decimal format. So we'll say a number, dot a number, dot another number, dot our last number. In this example, 208.123.45.18. Okay, that's cool. But again, why do we need this stuff? Well, layer 3 of the OSI model is our network layer, and we need to be able to connect to our network, and then of course outside of our network, so we can send and receive data with the world. And how this works is we route information from us to whoever, and our router is dependent on an IP address. Now there's this other thing that goes along with IP addresses called a subnet mask. And that's more for an internal organization, but there are 3 subnet masks I want you to remember. 255.0.0.0 is the subnet default subnet mask, I should say, for class A IP addresses. 255.255.0.0 is the default subnet mask for class C. And 255.255.255.0 is the default subnet mask for class C as in Charlie. So Alpha, Bravo, and Charlie have a default subnet mask. We are not going to go in more depth to these things in regards to having to subnet in A+. Therefore, I just need you to know that much right now. We'll talk a little bit more about it in a specialized section just for IP address classes and how subnets have any relation to it, but do not fear, you don't need to know how to subnet. If you have no idea what I'm talking about, when you get to Net Plus, we're going to learn this really cool thing called subnetting. And it takes a little bit of patience, but you'll get it, I promise. So let's focus on some other things that are absolutely required to get online. And that's the default gateway. Now, the default gateway when we're getting our IP address information is going to equal the IP address of our router, because that's the thing that gets us not only online, but to remote networks. It lets us communicate outside of our own network, aka the internet. We know that's what we want to reach. That's our goal. So, who gives us all this information? Well, that thing is called a DHCP, the Dynamic Host Configuration Protocol. In an enterprise environment, it is a special server or place on a server that distributes all of these numbers to all of the users that get on the network. At home, this is done by your router, that little multifunction device that is your firewall, it is your DHCP, it houses your DNS, and you just think it's a router, but it does so much more. So I mentioned class A, class B, class C. What does that mean? Well, it just means that we have different chunks of IP addresses that belong in different ranges. 0 through 126 is class A, 128 through 191 is class B, and 192 through 223 is class C. Now we're going to have a separate section that talks just about that, but I have this up here because those default subnet masks are important, and that's why they are still there. But never fear, I'll have lots of notes for you to take in a different section. And these are notes and flashcards that you will want to have. You need to know your IP address classes, both public and private, and I'll clarify that. as well as your default subnet masks, and those are on screen right now. So not everybody wants to write 255.255.whatever.whatever. So there's a shortened version of this that we call CIDR, Classless Interdomain Routing. CIDR. And that just means instead of 255.255.254.0 in the example you have on screen, I can actually just write my IP address, which is 192.168.12.0, and I can put this CIDR, which is the /23, and that equals the same exact thing as 255.255.254.0. So do you need to be able to add or subtract all of this good stuff in binary? Nope, not at this level, not at all. You just need to know that there is a shorthand for writing out subnet masks, and we call it CIDR. Oops. All right. Now I mentioned IPv6. IPv6 is longer, and it is the thing, the magic, the numbers that is going to, and is already, to be honest, solving our IP addressing needs. Now, we did run out of IPv4 addresses a long time ago, and that's why we have these things called private ranges in our IPv4 addressing scheme. But IPv6 is going to be the fix to all of that. There are actually some countries right now that are 100% running on IPv6, and they don't even touch IPv4 anymore. So you got to be aware of that this is the future of IP addressing. And if you're going into networking or Cisco, this is going to be more and more important as time goes on. So why is it so long, and where did the letters come from? Those are the two best questions you could be asking at the A+ level. Well, it's longer because we needed more addresses. But the letters is the magic here. IPv6 is not written in binary. It is written in hexadecimal, or hex for short, which means we have more characters to play with. Now, binary gives us ones and zeros. And decimal format, which is what we normally use with our math and our normal number system, is 0 through 9, which is actually 10 characters, right? Because 1 through 9 and 0. All right, so we needed some more characters to play with. I've got 0 through 9. What happens if I want to use the number 10? Well, that takes up 2 spots, which is totally against the rules here when I'm trying to write out an address. So the number 10 here is what A equals. So A equals 10, B equals 11, C equals 12, D equals 13, E equals 14, and F equals 15. And that's pretty much where it stops. Hexadecimal, hex is 5, right? And we have 15 characters available to us in the hexadecimal format, 0 through 9 and A through F as in foxtrot. So what's the big difference between IPv4 and IPv6? Well, the first thing you'll notice is it was much longer, right? So IPv4 has 32 bits, 32 ones or zeros, and that's all. We can't go beyond that. That's why we don't have enough. IPv6 has 128 bits, which is a lot more and will cover us for the rest of our lifetime and the next few generations. I'm sure of it. I say I'm sure, but I'm not really that confident, to be honest, because we're using these things up like crazy. All right, the other considerations or differences. IPsec stands for IP security. It is definitely optional for IPv4, but it is already built in and required for IPv6, meaning that our data is much more secure when we're on an IPv6 standard. Also, when we're looking at deployment, the whole world that was networked, connected to the internet, transferring data, they all used IPv4 at some point. IPv6 is not necessarily in its infancy, but it's not really widespread as far as who's using it yet. Like I said, there are a few countries that are already 100% converted over to IPv6, but the whole rest of the world is not quite there yet. So we're on our way, slowly but surely. All right, so I had mentioned this thing called private addressing and public addressing, and I'm going to go over it in much more detail, but let me give you a summary here. Private addressing are the IP addresses that we use for the nodes within our network. They need IP connection, they need an IP address, but they don't necessarily need their own individual unique address to show the world. They just need an inside address. Let me give you an example. When you go to school, or when you did go to school, you went to the University of, or this and that high school. Okay, that's cool. And if somebody asks you where you went to school, you would tell them the name of the high school or the college or wherever you were going. You did not necessarily tell them what room to find you in during different times of the day, and I'm sure you did not tell them what seats you were in and what the name of your instructor was at every point in time, especially if you didn't know them. So the private address is what seat you're in, what room you're in, what building you're in your school, not necessarily just the school itself. That's what the public address is for. So the public address is just the name of the school, and all the kids within the school, and I say kids as students or participants, and it includes adults, I'm sure, but all the students in the school have their own seat and have their own classes. But that's a little bit too much detail when somebody just asks you where you went to school. So think of it that way. The public address is what connects computers to the internet, whole networks. But if you're just communicating from one student to another student, seat to seat, or maybe between one class and another class, you don't necessarily need a public facing IP address. So we saved a few of them with private IP address scheme per se. Now, a PIPA and loopback are important numbers, and you'll need a flashcard. You'll want to memorize these. A PIPA stands for Automatic Private IP Addressing, and you're going to get one of these numbers at any point you cannot connect to your DHCP server, whether it's your client, aka your device, that can't connect, or the DHCP server is actually down. Whatever the reason is, if you don't get an address, you're going to be assigned a PIPA address. And the numbers that this starts with are always 169.254. 169.254.something will be your IP address if for any reason you don't get one assigned to you from your DHCP server. Now, a loopback address is very different, but just as important. 127.0.0.1. Just write that down. 127.0.0.1. This is a loopback address, and we use this to test our own connectivity. I want to make sure that my laptop is online, my PC is on the network, that the NIC itself, the network interface card, is connected. It's on, it's operational, and this is how I test that out. 127.0.0.1. All right, so those are all for IPv4, but IPv6 has the same numbers. They're just going to look a little different. So if I need an APIPA address, meaning my DHCP server is not working or my client cannot connect to my DHCP server, then I'm still going to get an APIPA address, but it's going to be F as in Foxtrot, E as in Echo, 80, ::. FE80 is the APIPA address for IPv6. Now, a loopback address, again, you're going to be able to have one of these in IPv6. It's just going to look a little different. And the address there is : :1. Now, let me go back a few slides and see why we're using colons. Notice here that the example address is 2001 : 0 Delta Bravo 8 : Alpha Charlie 10 : so on and so on. I won't read the whole thing. But what I need you to notice is that we don't use dots like IPv4. We use colons. In IPv4, you'll see that we have between one number and three numbers, dot, another number, dot, another number. Those numbers are only going to be between 0 and 255. That's as big as a number can get, 255, dot something else. Never going to go above that. But in IPv6, we can have up to 4 characters and then a colon instead of a dot. Random, but important, so take note of it. All right, let's get back on track. So we talked about DHCP a bunch, and we will talk about it some more. But do we have to rely on this DHCP server thing? Not necessarily. We can statically or manually assign our IP address information. Static and manual are the same, and dynamic and automatic are the same in IT. So if I'm statically assigning an address, that means I am manually inputting the information that I want a computer to depend on, meaning I'm going to tell it what its IP address, I'm going to tell it what the subnet mask is, and I'm going to tell it what the default gateway is. And don't forget, your default gateway is the IP address of your router. All right, so that's static. Manual, static, that's good for security and really small networks, but when you've got thousands of users, nobody wants to deal with that headache. And that's why we have automatic. Dynamic host configuration protocol means that whenever a node or device or thing comes online, is ready to get their addressing information, it's going to connect to the DHCP server and say, hey, I'm here and I need an IP address. Can you give me the numbers? And the DHCP server is going to give it the IP address, the subnet mask, and the default gateway information. Again, really quick, what is a default gateway? All right, hopefully you said something around the IP address of a router, because that's exactly what I'm looking for. But anyways, it'll give all those numbers out to each device that comes onto the network, and then that device can reach not only within the network and communicate with other computers, but it can reach outside of the network, aka send and receive data through the router. So DHCP settings, take a look here. One, it needs to be enabled, meaning that it's on. It'll give you your IPv4 information, and if you have an IPv6 enabled router, then you'll get IPv6 information as well, even if you don't use it. This is the numbers that in your command line screen that you looked at when you typed in ipconfig. If you haven't done that already, I'd love to have you do that now, because I want you to see the information on your own system. If you're on a Windows system, hit your start button and type in CMD, and you'll see this thing called a command prompt. Go ahead and open it. And when you do, you'll get a screen that looks kind of like this. And you're going to type in ipconfig, C-O-N-F-I-G, no spaces. Hit enter for me and let the magic happen. Your IP address will be on screen. You're gonna get some information about your MAC address, your subnet, your router IP address. You'll see some IPv6 information. It's really cool, and you should definitely know what's going on your own network. Now, if you're at work, you can still do this. You just might not see as much information. Totally fine. Start getting used to the command prompt. Don't let it scare you. All right. So now that we've talked about that, I want to talk a little bit about DNS here and what it does for us. Now, we touched on this briefly before, and if you remember what it is, then this will be review plus a little bit more information. But DNS stands for Domain Name System, and that's what allows us to put in just a domain name. Google.com, IMIT.com, Cisco.com, wherever you may be headed. Now, our computers don't read domain names. They want nothing to do with them. So DNS takes care of all of those details for us. What our computers want is an IP address. They want the IP address of the web server for the domain that you're trying to get to. So if I want to go to cisco.com, then I need to know what the IP address is. And I don't know about you, but I don't know what the IP address is for Cisco's website. Let me take a look. Even if I Google it, it's not necessarily telling me. Well, it's okay. I want to know at this point how it is I can get away from having to know the IP address of, well, any website, right? Because nobody wants to memorize IP addresses for every website. We have domain names for that. So anyways, what does our DNS server do to prevent having us to memorize all this good stuff? Well, it's going to translate the IP address to the domain name for us, so we don't have to memorize IP addresses. And I'm actually going to go into my own command prompt here And I'm going to find out what the IP address for Cisco is. And of course, it is giving me IPv6 addresses, but it'll still work. So what I'm seeing here is that it's connecting to a web server at 2600:807:22 Foxtrots. And then I got all the way to Cisco, and we're at a 2001:420:1101:1. Woo, I just said a bunch, but I want to show you what I did. I went and traced my route to cisco.com, and it's got a whole bunch of routers that it hit. But it was finally found, and this is the IPv6 address for the web server for cisco.com. So it took me a second to get to my example, and I was waiting for all of this good stuff to happen. But every IPv4 and IPv6 address is attached to something, and I specifically wanted to get to cisco.com, and this is the actual IP address of their website's server. This is where it's being hosted. So when I go to cisco.com, my computer is actually going to this IPv6 address. This is where it's going. This is what it reads. This is what it understands. It doesn't really understand what cisco.com is, but DNS handles that for us. It takes the domain name and it has a huge database of what IP address is connected to this domain name. So when I go to cisco.com, it has that IP address that was just on screen connected to it. So it knows where to go look. Now, you can have a DNS server, which is its own dedicated server to housing all of this information. But on a smaller level, you can actually have what's called client-side DNS, which means it's cached locally in your computer, right in front of you. So it will keep a record of the most often visited, meaning usually your email, some of your social media sites, whatever you do every single day. It's going to keep that information locally, so it doesn't have to depend on connecting to the DNS server to get you to your favorite websites. All right, that was a mouthful, and it's totally fine because DHCP and DNS are probably some of the most intricate things that you'll have to learn about on the networking side of this course. So now that we've gotten over the heavy stuff, let's talk about things that you probably already know about. Your ISP is your internet service provider. They're the ones that you're really excited about because you have great internet at home, and they're the ones that you complain to when your internet goes out. So ISP, internet service provider. And how you're connecting through your ISP might be one of many different ways. So you might be on a cable connection at home through your cable modem. You might still have DSL or dial-up if you live in more of a rural area that doesn't have fiber yet. If you're one of the lucky ones, you have fiber, Fios, Uverse, something awesome. There are a lot of options out there. There are still people that are connected via satellite, and these are really remote areas that just don't have the infrastructure laid yet, meaning not everybody in the world is connected via a cable modem. So be lucky that you're even able to stream this video, and be thankful that you're not in the middle of nowhere, not able to watch anything on YouTube or Netflix ever without hours and hours of buffering. All right, ISDN is a little higher end per se when it was new, and it carried both voice and data over plain telephone lines. PSTN is the public switch telephone network, which means normal old school legacy infrastructure that we still use today. Cellular connections, of course, is how we connect to our 3G and 4G data connections with our phone. This is over a cellular network system. And LOS stands for line of sight, which means you have to be within the line of sight of whatever you're trying to communicate with. Both devices need to see each other, and they can't have any type of obstructed view. I remember the old DirecTV commercials said that you just need a clear view of the southern sky. Well, satellite is one of many connection types that are line of sight, which is why when we have really bad weather, you may have an issue getting your signal for your GPS. And of course your TV. Now the last part of this section is TCP versus UDP. And we did talk about this when we did our OSI model review, but I'm going to touch on it again because it's a very important part of networking. Now that we already talked about getting data from point A to point B, that's cool. But how fast does it get there? And how do we know that it's going to be put together in the right order when it gets there if it was broken up into all these tiny little chunks? Well, TCP is what puts emails, documents, stuff that is important to be reassembled in the proper order. TCP handles that order. Now, it's a lot more complex and it's definitely a little bit slower, but it's really important when I send an email that all parts of my email get there and that all the text is in the order that I wrote it. I would hate to have only the, hey, how are you doing today? I'm too busy. And it skip a few sentences, maybe that said right now, but I'll get to it tomorrow. And then it just closes with, but I'm sure you'll take care of this and let me know when it's completed, right? Oh goodness, there's a huge email with all kinds of nice things in the middle, but if they only got the beginning and the end, well, we'd probably all be fired at some point, right? So TCP is what stops that good stuff from happening. UDP, however, is not going to hang out and put stuff back in order and care even if it missed a part. Well, why in the world would we want to send data and not have all of it make it there or in the right order? Well, when is the last time you streamed a live event? Maybe you were watching football or basketball or a fight, whatever it may be, or if you were on a phone call with somebody and that's like a live voice call, right? Would you rather, one of two things, would you rather your entire game come to a complete freeze because one of the frames were dropped? Meaning some guy's dribbling down the court and the basketball in your TV, right, on your screen, skips from when he hit it with his hand to when it hit the ground. And everything else in between was a few frames that didn't necessarily make it. Now, would you rather have your whole basketball game buffer for 5-6 minutes, multiple times a game? Or would you rather just skip those few frames and jump back to a live feed? Same thing with a phone call. If I said, hey, how are you doing? And how got dropped. So what you heard is, hey, are you doing? Well, you could either figure out what I said or you could ask me to repeat myself. That's not that difficult. And it's much better than the whole call coming to a stop, the data trying to rebuild itself. It might not ever be able to rebuild itself, to be honest. Those frames may just be lost in space. And then you never have more of a call. So it drops and you have to call them back. That to me sounds like an epic headache. So when it comes to things that are live or more important for the full picture versus every single piece of data coming together perfectly, well, that's where UDP is going to shine. It's less complex, it's much faster, and it's not as reliable, but we use it in places where it's okay not to have 100% reliability because my football games are already 3 hours long. I don't need them buffering. I don't need them to be 6 or 7 or 8 hours long. I'm good with the 3 hours considering they only play for 1 hour anyways. All right, that is what we're going to call the halfway point for this lesson. You have learned a lot about networking. You've learned about cables. You've learned about connection standards, IPv4 and 6 addressing, as well as DNS and DHCP. These are all important things to getting our devices and ourselves online, not only within our network, but out to remote networks as well. This is an important video, and there is a little bit more that we need to talk about as far as port numbers and, of course, the physical devices we use to troubleshoot our networks when things go wrong. And that is what we are going to cover next. So study, and I'll